If you were to give a meaning to the ratio of the change of capital E and the change of t, based on the mathematical convention we have established so far, you could have tried average rate of change of energy in respect to time. It is an average rate of change because there is no mention that the delta t is almost zero. It would have been an instantaneous rate of change if it had been. We had been using capital E for energy before, but so far it always had a subscript to identify which type of energy it was, like EK for kinetic energy, EG for gravitational potential energy, and ET is for total mechanical energy. It is on purpose that I do not specify the type of energy here, so that the following discussion would be about any type of energy. For example, if an object is slowing down, the kinetic energy is decreasing, so delta EK is negative, so is its average rate of change. In the case of an object going up, the gravitational potential energy would increase with height, so the delta EG is positive, so is its rate of change. The total mechanical energy is constant in the case of conservation of total mechanical energy, so the rate of change of the total mechanical energy is zero. So the kinetic energy goes down just as fast in value as the gravitational potential energy goes up. Since energy is a scalar, so is its average rate of change in respect to time. Its measurement unit is joule per second, which is the same as 1 watt. The letter W here is an abbreviation for the measurement unit watt, and not to be confused with the variable name for work. The measurement unit of watt is in honor of James Watt, a mechanical engineer that improved the steam engines in the 18th century. He was responsible to define the measurement unit of horsepower for the imperial system of units. 1 horsepower is the rate of change of the gravitational potential energy of a 549.4 pounds weight that is lifted by a horse through a vertical distance of 1 foot in 1 second. Converting the pounds into newtons and the foot into meter, we can arrive at a conversion between horsepower and watt of 1 horsepower being equal to about 746 watts. Power is a positive ratio of energy and time. The energy could be a change of a type of energy or the work done by a force. There is a disregard for the sign of the change of energy or the work involved, which makes power a positive scalar or zero. We could write equations for power this way, but it is customary, because of its definition, that the absolute values are omitted. You just need to remember that the numerator needs to be positive. For example, a nuclear station provides energy by converting the energy released in nuclear reaction to electrical energy. There are numerous transfers of energy at the nuclear plant, but the end result for the customers of Pickering Nuclear Station is a total of 3,100 megawatts of power. This is 3,100 times 10 to the 6 joules of energy every second. When a 60-watt light bulb is attached to a normal household electric circuit, it means that 60 joules of energy is transformed into light and heat every second. We need to find the minimum power of the motor necessary to perform the task of lifting an elevator and its occupant of total mass m to a different height. We will choose the level of zero height at the initial level of the floor of the elevator. The floor of the elevator would be at the final height after the time interval delta t. The givens are the initial height, the final height, the mass of the elevator and its occupant, and the duration of the time interval. The power is the ratio of the change of energy necessary for this task and the time it takes to do it. The change of energy necessary for this task is the change in gravitational potential energy, which is evaluated this way. Recalling the definition of the change in height gives this. It is time to use the numerical values of our givens and use a calculator for the final numerical answer. Our final statement is that the average power output is 6.81 kilowatts, which is 6.81 times 10 to the 3 watts. In the previous example, friction was not considered. If there had been friction, the motor of the elevator would have had to provide more energy to deal with the work done by an applied force that needs to balance not only the gravitational force, but also the friction. What was calculated in the previous example is a power output for the task of lifting the elevator and its occupant. In practice, the motor would need to expend more energy during the same amount of time to end up doing the task. This power is called power input. Not all the energy provided goes to lifting the elevator. P out is smaller or equal to P in, never greater. Efficiency is a way to quantify how much the power output is different from the power input. We will use the string of letters EFF as a variable name for efficiency. Efficiency is the ratio of the power output and the power input, and is often expressed as a percentage. Efficiency can also be defined in terms of the ratio of the energy output and the energy input, because, after all, when using the definition of power, we can write this, which simplifies to this. Let us continue with the example of the lifting of the elevator and its occupant. Here is our list of givens again, to which we add the work done by friction. We will use the definition of efficiency with the ratio of energy output and energy input. If the motor has to deal with the friction of the elevator rubbing against its metal guides, it has to add the energy that would be lost to friction to the change of energy required to do the task. The absolute value sign is required to add a positive amount to the energy output. The output energy is the change of gravitational potential energy. Just one more step to simplify the expression by removing some mg, and then we can substitute the numerical values of the givens. The calculator gives an answer of 0.943, which in percentage is 94.3%. One of the specifications often assigned to devices is its power rating. This can be used to estimate how much energy will be used in its operation if you also know how long it will be in use. Essentially, the energy consumed by a device is equal to the power rating of the device times the amount of time that the device was in service. Here, we use the definition of power and isolated for the change of energy. Let us do an example with an amplifier that is used for 10 minutes. The givens are the power input and the duration of the time interval. We will use the equation relating the energy consumed to the power rating and the time interval that the device was in use. Next, we substitute the numerical values of the givens. Please notice the factor 60 that was needed to convert minutes into seconds, so that the measurement unit for the energy would be in joules. Removing 3 zeros to the final answer allows us to write it in kilojoules instead. This is our final statement. As human beings, in order to do tasks, we need a supply of energy. Our energy input is in the potential energy of chemical bonds of the food we eat. After all, a chemical reaction is the spatial rearrangement of the atoms involved. Each activity has a different power rating. More energy is consumed every second when you are playing basketball compared to walking. The power rating for walking is higher than it is for sleeping. The measurement unit for the energy in food is typically a calorie. Notice the capital C for the calorie because it is different from a calorie with a lowercase c. In fact, here is the conversion to the SI system. The reason behind this seemingly arbitrary definition for the calorie will be explained later. Let us do an example where we want to know how many food calories of energy will be used during a 20-minute walk. The givens are the power rating for walking and the length of time for the walk. We again use our relationship between energy and power and substitute the givens. The numerical answer we would get would be in joules, which we can write in kilojoules. Next, we need to convert kilojoules into calories by using this conversion factor. We can now express our answer in food calories. This is our final statement. Another typical measurement unit for energy is the kilowatt hour. This measurement unit is mostly used by electric utilities. Here is how it is converted to joules. In problems where the answer has to be given in kilowatt hour, it is useful to write the power in kilowatt and the time interval in hours. For example, here we want to evaluate how much energy in kilowatt hours is consumed by a refrigerator during a year if it turns on only for 5 hours each day, and that the power rating when it is on is 450 watts. The givens are the length of time that the refrigerator is on during the day and the power input when the refrigerator is on. Let us first write an expression for the amount of energy consumed in one day using our relationship between energy and power. But what we want is the annual consumption, which is 365 times bigger than the energy consumption for one day. Let us now replace the energy for one day with the expression we established earlier. Next, I have substituted the givens, and contrary to my habit, I have written the measurement units of the givens as well. Normally, to get an answer in joules, the time interval should have been expressed in seconds, not hours. I will change the amount in watt to kilowatt instead. Using these numbers leads directly to an answer in kilowatt hour. This is our final statement. Notice that you could just as well have found your answer in joules first by converting the 5 hours into seconds, and afterwards divide the answer in joules by 3.6 times 10 to the 6 to convert it into kilowatt hour. Your choice. This concludes this lecture about power and its relationship with energy. Next, we will look at how energy is generated for our daily use. This will be the subject of our next installment.